this program. I'm very grateful to you indeed. I am very grateful to my faculty colleagues and also to you students for coming here today. This could be my last seminar on this occasion, could be my last seminar in my lifetime here. So it is an occasion for me to remember. Now, I'll just open this. Okay. Right. The talk, well, it will be a slightly longish talk. It's intended to be a colloquium. So I hope you're not too hungry because khali pete physics hoy na.
How long is long?
Well, I think about 35-40 minutes. Is that all right? Yeah, I'll try. So what's there that is new about Albert Einstein? We've been doing things according to his diktat for many years. So I thought that it would be a nice thing to look at his legacy and divide it into what may be called the quantum legacy and the continuum legacy. And in doing so, I discovered that there is indeed a kind of dichotomy. A dichotomy, for those of you who might be a little worried about this English, is really not that difficult. It's the coexistence of things which have elements of a contradiction between them. So I'm going to try and argue that indeed his contributions have some dichotomy. Now what all of you have heard is that Einstein had some reservations about quantum mechanics. He did not feel that quantum mechanics is wrong, he felt that it was incomplete. And why so? And then from there, where can we go? Because that already was articulated in the late 1930s, I think 1939. So, unfortunately, there is a matter of pride in this, but I can't show you in full glory because we don't have Adobe Reader here. This is an animation. Now, the year 1905 is known as the year of miracles, annus mirabilis for Einstein, because in that year he wrote 5 papers which changed the course of physics altogether. Now, unfortunately, I can't show you the animation because this doesn't have Adobe. This basically is a grain of sand put in a beaker of water, glass of water. And then Mr. Brown in the 19th century was studying the motion of this grain of sand. Well, it will move because at room temperature it has kinetic energy, but what is the nature of the motion? And he was surprised. Remember, this is 19th century, and they never knew about molecules really at that time. And he was very surprised to find, but I can't show you, that the motion is a very zigzag kind of motion. A modern version of this motion, Brownian motion in 2 dimensions, has to do with this. So this is the kind of motion you will experience if you want to go to Belur station, not the Belur Math station, but Belur station, and had to go through a michil, a procession, coming in the opposite direction. That's the kind of thing. And if you have a train to catch, God help you. So the green point is the starting point, and the red point is where it finishes. You can see this, that is a very zigzag kind of motion. The motion is certainly not differentiable with respect to time. So you can't write down Newton's law to discuss this motion. The only way to discuss this motion is statistically. And it was first done by Albert Einstein. This is Einstein's formula. He wrote down the mean squared displacement, x squared, after a time t. And on the right-hand side, we have Boltzmann's constant. The temperature, of course, it depends on the temperature, divided by eta is the viscosity. If the viscosity is large enough. So if there's a very dense chill in front of you, greater difficulty. R is the radius of the particle, and small t is the time. Now, what does this tell us? This is, of course, old formula. This zigzag motion means that indeed the fluid medium, like people walking towards you, is not uniform. It's not a continuum. It is made up of molecules. And indeed, this description means that matter is discretely distributed in space. So the number of degrees of freedom of matter is countable as opposed to what people have been thinking for ages, that you have a continuum, which means that you have a non-countable infinity of degrees of freedom. No, matter is countable. Degrees of freedom are countable. And it was Boltzmann, another 19th century great person whom you have heard of, who talked about entropy related to irreversibility, related to probability, so things are not certain. You have to talk about probability, but this is classical statistical probability, not quantum probability, and related to countability. So things are discrete, they can be counted, something totally different from what people used to think those days. And Einstein's derivation of Brownian motion is basically a proof of the discreteness of matter. So this was a departure from what people have been thinking for a very long time. Next, something we all know, the light quantum hypothesis. So we begin with something that all of you know, the Maxwell equations. Well, these are the Maxwell equations, but these are the Maxwell equations not for continuous densities and currents, but for a set of charges. So of course, if you have a set of charges, they constitute a distribution. And that charge density will then be given by a delta function. I think all of you know what a delta function is. Similarly, in this second equation, it is a current. So you have a stream of charges moving at certain velocities, Vi. Okay? And here, what Einstein was quoted to say that, look, when you describe this, you can count the charges. There are n number of charges, right? But you can't count fields. You can't say I have 5 fields. You have continuous functions to worry about. Non-countable functions being generated by countable sources. So Einstein was very uncomfortable, as you can see from the quote. And in fact, he went on to say that this would actually lead to a contradiction. Now, people say that Planck is the father of quantum theory or whatever, but that's all wrong. Planck did what we in Bengali call backmara, which all of you know. Back calculating formulas to agree with an experimental result. That's what Planck did. And the funny thing is, Planck was not even aware of what he was doing, because he was a confirmed classicist. He loved classical things. He loved the continuum. In 1908, after the year of Einstein, Lorentz, another great scientist, told him, hey, Planck, do you know what you've done? Classical physics is almost dead. And Planck said, oh my God, what have I done? And then, of course, he had to convert, because by that time, the real father of quantum theory, Albert Einstein, had done everything. And Einstein told us something that we know, namely that if you look at a situation where you have the full conversion of light electromagnetism to matter, or the other way around, the full conversion of light into matter occurs in the photoelectric effect, and the other way around is what is called blackbody radiation. And these are precisely the two things which cannot be described by classical electrodynamics. You all know this, but this is what Einstein said. So basically, there's something wrong with classical electrodynamics, and you need to change it. What do you change? Well, this is Einstein's suggestion. 1905, he talked about photons. He introduced quanta of electromagnetism. The electromagnetic field is not continuous, but made up of quanta. And now things agree, because you have quanta charges, charge is quantized, you have quanta, the fields they produce. But how does it all work out mathematically? And poor Albert Einstein was at a loss. And he was at a loss because nobody knew quantum mechanics at that time, 1905. People didn't know how to discuss, how to quantize the electromagnetic field. And believe it or not, the world had to wait for 35 years before they actually recognized this, before people like Schrödinger and Dirac, well, not Schrödinger, Heisenberg, Jordan, Dirac, these people worked out quantum electrodynamics. So the next thing, so these are formulas that you know for light, worked out by Einstein. It's very easy. You can see all these formulas on the left, these two formulas. The left has a particle thing, and the right is the wave thing. But this relates the fact that waves must actually be made up of particles. So this is not duality. So now there's something again that you all know, and I wish I could show you the animation. Again, it doesn't work because we don't have Adobe here. This is just to show that there's a classical motion, which is the spring mass system, and then you have the quantum wave functions of a quantum oscillator, which lead to your tower of quantum states, okay? And I just wanted to show that these are very different motions. So that's the ground state, the first excited state, and so on. So I've plotted a few things. But the animation would have made things very clear. Unfortunately, we can't get there. Okay, never mind. Now, the reason I showed this is because there's this formulation of free photons, of light, which people calculated, like I said, 35 years after Einstein. Free photons, laser light, is made up of millions of harmonic oscillators. Now, some of you may be doing quantum field theory. Free photons or any fields can be described in terms of harmonic oscillators. And that's beautiful because you all know harmonic oscillators, you know the tower of states. For the fields, you just have one tower for every value of the momentum. Okay? And because there could be any momentum, you have an infinite number of tower of states, but they're countable again. So everything in the quantum domain is countable. This is something quite remarkable. All started with Albert Einstein. So, however, we're not really interested in free photons because I can't see free photons. Unless the photons hit our retina, there's light, okay? So basically, there must be interaction, and the interaction is between photons and electrons, and this is the subject of quantum electrodynamics. Now, this is a very, very difficult subject because just think of the number of photons and the number of electrons in this room. You would just give up and say, hey, ato beshi, it's impossible. But there it was another genius, Richard Feynman, who says, hey, wait. I think there's a trick to this. And the trick is to draw these diagrams. It's amazing. You just draw these simple diagrams, and associated with each diagram is a quantum mechanical amplitude. And from there, you can talk about squaring the amplitude, you get the probabilities, integrate the probabilities, you can have cross sections, which you can measure in the laboratory. But he was also able to show that these diagrams can be drawn as a perturbation series. Now, you've studied some quantum perturbation theory, I'm sure. So this is a perturbation series. The top panel is the lowest order, the second is a higher order. And you can go on and on, higher and higher orders in perturbation theory. I'm not going very fast, so I have to speed up a bit. The only thing I wanted to show you here are the people involved. So there's Feynman sitting down there with some colleagues. So the reason that I wanted to show you this is the calculation that these people did of the anomalous magnetic moment of the electron. Now that calculation has been perfected, and you can just see, if you see the numbers, so the top is the perturbation series in alpha, which is the fine structure constant, followed by a line, which is the experimental number, and the agreement of theory to experiment is 1 part in 10 to the 9. We all know falsehood and truth. That is truth for me. The agreement of theory and experiment to accuracy of 1 part in 10 to the 9. This is absolutely amazing. This has happened once later on, but maybe I should not mention that. Otherwise, this is unprecedented in the history of physics. So this is a major success of perturbation theory. But you will wonder, oh, it's all very fine tricks to draw photons interacting with electrons, but where are our old electric and how do I recover them from the description in terms of photons? I don't know why this is creating some kind of noise. Maybe he doesn't like me. Maybe I just switch this off, I don't know. Anyway, this was done. Well, to do this, we saw that field theory is described by harmonic oscillators. So we go back to the harmonic oscillator, the quantum harmonic oscillator, ask the question, when you were children, not really little children, but in class 9, 10, 11, you did the harmonic oscillator classically. and you got a solution x is equal to x naught cosine omega t. On the other hand, you worked out all those wave functions for the quantum oscillator. Oh, here, okay. Yeah, maybe you're right. So the point is, how do you recover x equal to x naught cosine omega t from the quantum description? And there it is. This is the theory of coherent states. Okay? So you realize that your occupation number states, the ones that you use in quantum mechanics, are not enough. You have to take an infinite linear combination of them. And if you take the expectation value of the Heisenberg operator x of t between these coherent states, then you do get your old high school formula back. So once you have it for the harmonic oscillator, you can think of generalizing it to electrodynamics. Okay? These are also the minimum uncertainty states, these coherent states. I think you must have studied coherent states in quantum mechanics in your class. These are the two gentlemen, especially the left person. I really admire him. His name is E.C. George Sudarshan. And he is the one who is responsible for showing us the way to extract classical electromagnetic fields from the photon description using electromagnetic coherent states. Unfortunately, the man on the right got the Nobel Prize. Now, Nobel Prize is politics, which I don't understand. So continuum fields and classical electrodynamics emerge from the discrete photonic description in the semi-classical approximation. Now, I shall go on to, so this was the legacy, quantum legacy that Einstein left, and I've just followed it up to where it is sort of today. But I now go on to the continuum legacy. The continuum legacy, I shall go straight to this. This is special relativity. This is the light cone, the magenta lines. Okay, so I just wanted to say one thing. This is also something that you know. You see, Einstein was a light chaser. He was fascinated by light. And that's not so uncommon in this part of the world, because we have another guy who's not a physicist who was also a light chaser. His name, of course, is Rabindranath Tagore. I mean, you know, if you don't believe me, take up your Sanchoita and count the number of poems he has with the word alo or alok in it. Okay? It's enormous. So these guys met, and I think all they did was discuss the nature of light, you know. Throw light on the light. Light is something very fascinating indeed. So I shall not say much about this, except to say one thing, that Einstein was not the first to discover, but Minkowski. These are beautiful stories, but I don't have time to tell you these stories. Minkowski was supposed to be Einstein's teacher, but then he was absolutely unimpressed by Einstein and asked him to go away. But then when Einstein discovered his special theory of relativity, it was Minkowski who found the mathematical structure. What we call Minkowski space is this. And what he immediately could see, Minkowski being a mathematician, is that the geometry of space-time is very different from the geometry of flat space, Euclidean space. It's non-Euclidean geometry, and that the easiest way to see this is these magenta lines represent path of light, and if you take 2 points on it, the space-time distance between them, what Aditya called the metric, actually vanishes. Now, if you have Euclidean space and the distance between them vanishes, one point has to be on top of the other, but not in space-time. So space-time geometry has to be different from the Euclidean geometry that we've all studied. Right. So Einstein continued to chase light in the presence of gravity, and that led him to the principle of equivalence, which basically relates to something called the happiest thought of Einstein's life. He called it the happiest thought of his life, which is to say that you can switch gravity away. And the easiest thing to do is to climb up some tall building, enclose yourself in a cage, and have somebody push you over. Of course, this guy is not your friend, because you know what's going to happen after that. But then, suppose you take out a pen or some chalk or some material and let it go, you will see that that object is not moving with respect to you. And of course, I see from outside and say, oh my God, pore jache, but that's beside the point. So during the time you don't hit the ground, it is beautiful. And now Einstein discovered that using the principle of equivalence, basically equivalence principle means that there's an equivalence between acceleration and gravity, which translates to an equivalence between the masses, the gravitational mass and the inertial mass. Further generalization, and Einstein did a leap on that, he just said that all frames, irrespective of whether they're inertial or not, are equivalent. The physical laws must be the same in all frames. That's quite remarkable. But using that, the physics consequences was that you could show that light must bend under gravity. Now, everything, of course, follows a curved path if you have a force pulling it. But the great thing of Maxwell's electrodynamics is that light does not have mass. Light is very, very light, does not have any mass. So why should gravity pull it? This was a big mystery. And the only way Einstein resolves this mystery, he could show this thing when he showed that the light ray must bend under gravity. The only thing that needed to be argued was that there is no force involved. Whatever is bending the light has actually curved the space-time around it. So the Earth curves the space-time around it. Moon enters this space. There is no force on the moon, but the region has a curved geometry. So what will the poor moon do except follow the curved trajectory? Similarly, the Earth going around the sun does not happen because the sun exerts a gravitational pull. But all the sun does is to curve the space-time around it. And the Earth, in its own wisdom, has to follow this. This is the same thing that when you go to New Jalpaiguri station, you can sometimes, earlier days, you could see the Kanchenjunga, but you cannot go to the Kanchenjunga like that because the geometry is like that. Okay? Likewise, if you there at the last bench wanted to come and give me a box for some reason, you got bored with my talk, you have to come along a curved path because of the geometry of this room. Okay? If you try to follow a straight path, your friends will object very strongly. Okay? Light changes color. Already Aditya mentioned this, called redshift or blue shift, depending on the source, whether the source is approaching or receding. So this is also something which Einstein discovered. Light is massless, and therefore the geometry is curved. And of course, there's something very funny, because in any lab, light will travel always at 3 lakh kilometers a second. So what we have is space-time is locally flat, but globally curved. And as a result, we can use the fact that it is locally flat means that we can use special relativity to do GR, general relativity. How? Well, there, these are the light cones. At each light cone, you follow the laws of special relativity. But if you want to compare one light cone to another, you can see a relative tilt in the light cone, and the tilt has to do with curvature. The larger the tilt, the bigger the difference in the curvature. So this one and that one are much, there's a lot of curvature in between. And this is the reason why all particles have to follow curved trajectories, okay? Because of the tilt of the light cone. But within any light cone, you can see light will travel along the edge of the light cone, and you and I will travel through the middle, okay? Good. So this is Einstein's, what was the last? Yeah, okay. Something I already mentioned. Who curves space-time? Anything which has energy and momentum density, like light. But if it's light which is bending space-time, you know that light means light waves. We are not talking of static electricity. We are talking of light waves. So look at that equation. The right-hand side, you have something dancing away in time, electromagnetic waves. The left-hand side has to dance in unison. There's no choice if this equation is to hold. What does that mean? That means space-time geometry is dancing, it's dynamical. That's the essence of general relativity. So I said this, so it's not just mass, but energy and momentum density. But the most important thing is space-time geometry is dynamical. Matter tells space-time how to move. Space-time tells matter how to, well, one is curved, the other is move. But we have experimental observational evidence of a dynamical space-time. Already mentioned by Aditya, gravitational waves. Now I get very emotional when I think of gravitational waves, because as you know, I'm 65, and I could have easily died without having seen gravitational waves, but I have lived to see it. And we never thought that binary black holes existed in nature. They existed mathematically, of course, in GR, but now we know that they are a reality, and we would never have seen them had it not been for the detection of gravitational waves. So my God, this field is incredible. Gravitational waves is everything. It's a sense of GR, because it gives you the dynamism of space-time geometry. When you say gravitational waves, when it arrives here, it changes lengths and times according to the wave profile, and that's a dynamical relationship. Then we have expanding universe. Aditya already mentioned it. Universe is expanding. Now the universe expanding, what is expanding? It's the geometry. You have an expanding geometry of the universe, like a balloon with two ants on it. You blow the balloon, the two ants drift apart. The balloon is space-time geometry. This is a crude approximation, but that's really what it is. And then, of course, Alok talked about black holes. That's the other dynamical element. You have a star which is collapsing. Unfortunately, again, I can't show you the animation. The star is collapsing under its own weight, and it becomes something very simple and yet something very dangerous. Because if you get into that, you can't come out. That's called a black hole. Okay, so the dichotomy. Well, I'll come to a black hole a little bit. Maybe I'll ask for 5 to 10 more minutes if you don't mind. Anyway, we started a bit late, so I guess it's all right. You see, even Einstein formulated the special and general theory of relativity. He attributed them a kind of pristineness. I mean, that is obvious when you study these theories. The solutions are exact. So there is something pristine about it. He felt he was talking to the Uparwala through some hotline or something. But on the other hand, he also made contributions in the quantum domain, and in that he made beautiful approximations, but approximations nevertheless. So he always felt that these approximations, this is the way I interpret it, these approximations are tentative. They have to do with the fact that you don't have the mathematical apparatus to give you an exact description. So they are really tentative. And therefore, the statistical aspect is something which is there because they are tentative. You have to do this. Now, the point is that if something is statistical, like the formulation of quantum mechanics, the Copenhagen interpretation, Einstein's misgiving was that it can't be fundamental, like my theories of space-time. It is not as fundamental as special and general relativity, because I'm using a statistical formulation. I don't know enough about the mathematical structure to give you an exact deterministic description. I think this is what he must have felt. But hey, wait, we must look back at what he said. We must look back at critically. And if you look at Einstein's equation, left-hand side has geometry, space-time curvature. The right-hand side had the energy momentum density. We all know that the energy momentum density can't be a continuous function. Matter energy is quantized, momentum is quantized. So just like the currents and charges in electrodynamics, the right-hand side of Maxwell's equation is discrete, is countable. Very, very large number of particles in the universe, no matter how you characterize them, but still countable. We do count, as Aditya's talk we saw, we do count the number of photons to the number of baryons, for instance. That ratio gives us an idea of baryogenesis. How good is this baryon-antibaryon asymmetry? So we have an equation just like Maxwell's equation. The right-hand side is countable. The left-hand side is a continuum geometry. This was Einstein's assumption, that the left-hand side has to be a continuum geometry which could be curved. So look, we are getting to the same kind of problem that Einstein thought about when discussing Maxwell's equations. This is a formula which you must have seen, those of you who studied GR. This is the energy momentum tensor for n number of classical particles. And you can see the delta function. So you can see the discreteness right there, the discontinuity right in front of you. And if you use that to compute the curvature tensor, the Einstein curvature tensor, which represents curvature of space-time, you can see that I have discreteness on one hand and the continuum on the other. Okay. So I asked the question, just like Einstein, how can discrete bits of matter and energy produce a smooth continuum space-time geometry? And I recall those things, but Einstein was very sharp. Immediately he referred to experiment, which underlines the need for doing experiment in physics. He said, experimentally, we know that there will be contradictions for which classical electrodynamics will fail. I'm sorry, I apologize to Bobby, because he's teaching the first year's classical electrodynamics. To talk about the limitations of classical electrodynamics in the middle of the semester is not a good idea, but I think you will not be bothered too much about it. You'll learn everything later on anyway. The question is, are there contradictions for Einstein's equation? The answer, I think, this is again something that I've thought about, you have to look at situations where you have full conversion of space-time into matter, and the other way around. And we seem to have both of them. The conversion of matter into space-time geometry is called a black hole. You have a star that collapses under its own weight, then there's nothing, no matter anymore. All you have is curved geometry, very curved. It's infinitely curved at the singularity. I'll come to the singularity in a moment. But just to underline, we also have the other thing, which briefly was mentioned in the talk by Aditya. And I think it's a conversion of space-time geometry to matter. And of course, both these are examples of space-time singularities in general relativity. And a space-time singularity is a contradiction because it contradicts the fact that you have a space-time which is a smooth continuum, everywhere differentiable. You can't differentiate at a singularity. Again, I can't show you this picture, but this just shows how collapse happens. And I just wanted to say that collapse is where the volume of the star goes to 0. So if it had some mass to begin with, the density shoots up to infinity. And if you believe in Einstein's equation, then curvature must shoot up to infinity. And that makes this equation totally meaningless because you don't know what infinite density means physically. You don't know what infinite curvature means mathematically. So if you follow Einstein, you're led into meaninglessness. Okay? Now, singularities are not uncommon. They occur in electrodynamics. If you look at radiation reaction, you'll probably study that with Bobby in the first year. But this is far worse because it describes the breakdown of all laws of physics. And you can see that from this, but again, I shall skip it. This is due to the work of Rai Chaudhuri. We have a beautiful description of what singularity means, and now there are powerful theorems to describe it, but let me not get into that. The other conundrum, I'm very thankful to my, well, should I call you a former student or still a student? I don't know. Alok Sinha, who described to you this other conundrum for a black hole, and these are the laws of black hole mechanics. First of all, there's this area increase theorem. The horizon area can never decrease. Now that immediately rings a familiar bell with thermodynamics in mind. All of you have studied thermodynamics in college, and you know the second law of thermodynamics states that entropy can never decrease. Hey, but wait, how can I talk about entropy? To calculate entropy, we need microstates. And you know that there's a law given by Boltzmann that the number of microstates, the logarithm, gives you a measure of the entropy multiplied by the Boltzmann constant. But we have classical geometry for a black hole. There's only one state because these black holes are exact solutions of Einstein's equation. They're very, very simple objects mathematically. So there's only one state, they're exact solutions. And the log of 1 is 0. So classically it is impossible for black holes to carry entropy. And these laws, which already Alok showed you, they only reinforce. You have laws coming from general relativity, purely from general relativity, which on the other hand seem to imply that they have a statistical thermodynamic character. And everybody, including the authors of these, which included Hawking and the two other very well-known relativists, they said that, hey, look, this must be some sort of a coincidence. Because in general relativity, we don't have microstates. So how can there be thermodynamics for black holes? And here it was a young student by the name of Bekenstein who said that if you take Parthasarathi and throw him into a black hole, what happens to Parthasarathi entropy? He was outside. The outside entropy has decreased. And that is a violation of the second law of thermodynamics in a universe populated with black holes. So he said, no. The only way out, he said, is that black holes must themselves carry an entropy. And that, in order to agree with the laws of black hole mechanics derived from GR, must be proportional to area. And he said that the only source for these must be in quantum gravity. So already, unlike what I think Alok was not right, the idea of quantum gravity being important for the black hole entropy problem came actually from Bekenstein. Okay? It was the idea. He did not have any derivations. It was just physical intuition which led him there. So basically, what I wanted to say is just this, that the dichotomy, okay, that Einstein found with the Maxwell's equations, and he had to talk about photons, continues to general relativity, and you have to discuss a quantum theory of gravity to get away from it. Unfortunately, unlike quantum electrodynamics, we did not have that so much time for evolution of quantum gravity. We have had a few years. There are some serious proposals which I have listed here, but none complete. Okay, so let me not get into quantum gravity because I can see that everybody, all of you must be hungry, and it's already 1:40. Basically, all I wanted to show here quickly is that we have a picture of what one quantum space looks like. Quantum space looks like a fishnet. This is one of the pictures. It's called loop quantum gravity. So it looks like a fishnet. Now, of course, if you have a fishnet, there are holes in the fishnet. And if you have holes in the fishnet, is that a part of the space-time? The answer is no. They're not part of the space-time. You only live on the fabric of the fishnet. So what are the holes? The holes are not a part of the space-time. So, hey, wait, that's weird. But it's not weird. Look at the fabric you're wearing. Put that under a microscope. Isn't the picture just like that? So would you say the holes are a part of the clothing? No, they're not. This is weird. Indeed, the weaves are the part of the clothing. And now all I wanted to say, because I don't have time, is that there's a mathematical description from this which enables you, this is the work that I have done about 18 years ago with a friend Ramesh Kaul, and we have a beautiful description whereby you can actually compute not only the entropy as postulated by Bekenstein and also corrected by Hawking, but a whole slew of corrections to it. And these corrections come because now we have a quantum theory, which Bekenstein and Hawking did not have. So there is progress. There is progress, and Alok mentioned Hawking radiation. Well, I could say a little bit about it, but maybe not today, about Hawking radiation. And Hawking radiation has this problem of negative specific heat, which he mentioned. So if you have a Schwarzschild black hole, the simplest black hole, it radiates, it shrinks, and then you begin to wonder how far will it continue to shrink? Will it disappear? Now, Hawking felt that it will indeed disappear. It's called evaporation. But if there is evaporation, what is left over? Hawking felt that all you'll be left with is some heat. But you started off with a star, which collapsed to form a black hole. And a star is described by wave functions that you know how to deal with. Heat is not. Heat is described by a density matrix. And the laws of black hole, laws of quantum mechanics, ordinary quantum mechanics, tell you that if you start with wave functions, you cannot end up with a density matrix. This is called the unitary evolution of quantum mechanics. So Hawking's ideas are in contradiction with the laws of quantum mechanics, and this is called the paradox, the information loss paradox. I shall not get into that, I'm almost done. So there is a description which can be, so this is my last transparency, I end with this. So we have situations where we are able to describe black hole entropy starting from a quantum theory. Then Alok already told you about how to discuss thermal stability of black holes. I have that there. They may be used to describe neutron stars, singularity resolution for black holes, some progress already. Loop quantum cosmology, maybe there is no Big Bang singularity. Maybe the universe, if you go back in time, the universe contracts, and then bounces back. The bouncing model of loop quantum cosmology. Information loss problem may not be out of reach. The fun thing is that we are now talking about a discrete space-time. So the Einstein continuum, which Einstein envisaged, is really an emergent phenomenon. It's an approximation. Okay, I'll stop here. Thank you very much.